chapter 2. So we're going to be reviewing chapter 2. I'm not going to do every single practice problem on here, but I will go over them somewhat quickly, most of them somewhat quickly. So first thing we talked about were conditional statements. So remember, conditional statements are if something, then something else. They're only going to be false when the hypothesis is true, but the conclusion is false. That's what we call a counterexample. So if we look at this conditional statement here, if today is the weekend, then it is Saturday. This would be a counterexample because it makes this part true. Sunday is the weekend, but this part is false. If it's Sunday, then it is not Saturday. So this is where we call this a counterexample. As long as you have one counterexample, we can say that this conditional statement has a value of false. This conditional statement is a false conditional statement because there exists a counterexample. It only takes one to disprove an entire conditional statement. All right, then we had the three related conditional statements, the converse, the inverse, and the contrapositive. This kind of talks about how we create them. Converse, we just switch the hypothesis and conclusion. Inverse, we negate them. And contrapositive is like a combination of those two things where we switch and negate. We'll go ahead and do an example of doing this here on the next slide. So I'm just going to go ahead and move forward. So here is a conditional statement. If you live in Urbana, then you live in Illinois. And we're going to write these three statements. So the converse is achieved by taking our hypothesis and our conclusion. So this right here is our hypothesis, and this is our conclusion. So the converse, we switch those. So it's if you live in Illinois, then you live in Urbana. The inverse, we keep the order the same as the original, we just negate them. So we say if you do not live in Urbana, then you do not live in Illinois. And then for the final one, we have to do both of these two things. We have to switch the order and negate. So if you do not live in Illinois, then you do not live in Urbana. Okay, so the next part of this was to decide whether these statements were true or false. I like thinking about these in terms of Venn diagrams. I think this makes a lot of sense here for this particular problem. Remember, you can always take a true conditional statement and write it out as a Venn diagram like this, where your conclusion is on the inside, so you live in Illinois, and your hypothesis is on the outer circle here, so you live in Urbana. Right? Oh, my fault. I switched those two things. I don't know why I did that. I don't know why I switched those. Your hypothesis is on the inside. Your hypothesis is on the inside, so that you live in Urbana. And your conclusion is on the outside. You live in Illinois. So in this case, there are, hopefully someone in the chat was correcting me with that. Yeah, so there can be some technicalities with this one, because there are some Urbanas in different states. Let's just assume we're talking about this Urbana, just to make this a little bit simpler, because you're right. If there's like an Urbana in Ohio that I know of, and I think there's another one too, but let's just assume we're talking about this one just to make it a little bit easier. So in this case, if you live in Urbana, then you must also live in the state of Illinois. So this original one would be true if we're trying to keep it easy and only talking about, the Urbana that we all go to school in. The converse, if you live in Illinois, then you live in Urbana. This one would be false. We could think of a bunch of counterexamples. Any other state in Illinois would be a counterexample for this. So easy one would be, just one counterexample would be like Champaign. Champaign is in the state of Illinois, but it's not in Urbana, so makes that one false. Next one, if you do not live in Urbana, then you do not live in Illinois. Again, we can think of a counterexample here. We can think of something that's not Urbana, but that is Illinois, which again, I guess another false. This would, Champaign would be another counterexample for that. It's not Urbana, but it is in Illinois. So it makes the hypothesis true, the conclusion false. Last one, this one's always pretty tricky to evaluate, but if you do not live in Illinois, then you do not live in Urbana. Well, if you're not inside of the state of Illinois, then there's no way you're going to be inside this little bubble here that is Urbana. So this one would be true. There's always a couple of these that are connected. These two are always the same. If one of them's false, the other one's false. And these are also always the same. You don't need to know that necessarily, but the original conditional statement and the contrapositive will always have the same truth value. Same with the converse and inverse. Again, not super important that you know that part. We didn't go super far into truth values like we have in past years. So make sure you can write them. Make sure you can decide whether they're true or false. That's what I would say. All right. Then the next thing we did were algebraic proofs. So we used these properties of equality, plus we also had what's called the distributive property. Distributive property is not technically a property of equality. It's a property of multiplication. So that's when you have something on the outside of parentheses and you distribute it into everything on the inside. So like this. Useful, we use it when we're solving equations a lot. And that's what we talk about with algebraic proof. Algebraic proof is basically where we're solving equations using the distributive property and mostly these four properties of equality: the addition property, the subtraction property, the multiplication property, and the division property. These ones down here, in particular, these last two are going to be used a lot when we're doing geometric proofs. We'll use transitive property or substitution property, mostly with geometric proofs. I don't think we'll use them in algebraic proofs, really. Unless our algebraic proof involves like the segment addition postulate or something. All right, let's go ahead and do an example of an algebraic proof. Or let's look at an example of an algebraic proof. So there's a common misconception that I see people make with algebraic proofs. And I kind of try to write it out here on the side. The reason, so what you write on the right-hand side should be how you got to that step. So for the first one, you got this because it was given. The next one, we're doing the distributive property here. So we got to this equation by using the distributive property. We took that 2 on the outside and distributed it. That's how we got here. That's why distributive property is our reason. Same here. We got to this step by simplifying. We added the 4 and the 10 on this side of the equation to get 14. We got to this equation by using the addition property. We added x on both sides. We got to this step by subtracting on both sides by using the subtraction property. And we got to this final step by dividing both sides by 7, the division property of equality. So you want to use how did you get to that step? You can show your work in the algebraic proof. That's definitely encouraged. Show the arrows for distributing, show adding on both sides, show subtracting or dividing, whatever we do. But remember, the reason will be how you got there. All right. So let's do one of these. Let's do I want to do this one right here. So I'm actually gonna write this. Negative. That is not what I wanted to do. So this will be my given equation: negative 3 x plus 2 I'm going to cover some stuff up. Oops. Just so that I can solve this and minus x. And this is my given. So I'm going to go ahead and do this one as our proof example. With proofs like this, you always start with your given. In this case, it was the equation. And the reasons are going to be our properties of equality or that it was given to us. Okay. So first step in this equation, well, equations in general can usually be solved in multiple different ways. I'm going to do it in this particular way, but it's totally up to you. I'm going to start by distributing. I think that's probably just a common step that people will make here. So we'll end up with negative 3x minus 6 equals 16 minus x. And that is the distributive property. All right, then what are we going to do? Here's where we really do have some choices here. We could either get all our x's on one side, all of our numbers on one side. We could either put all our x's on the left or the right, numbers on the left. A lot of options here. So I'm just going to put all my x's on the left side. So I'm going to do plus x. I'm going to add x on both sides. So that would become negative 2x minus 6 equals 16. I got there by doing the addition property of equality. Okay, now once I've done that step, I kind of am limited in terms of what I need to do because I want to get all my numbers over to the right. So I'm going to add 6, get rid of that. So that gives me negative 2x equals 22. That was again the addition property of equality because to get here I added 6 on both sides. And then to get x all by itself, we just need to divide. So we're going to divide both sides by negative 2. That's going to mean we are using the division property of equality to get x equals negative 11. So that was like a 1, 2, 3, 4, 5, like 5-ish step proof, not too long. There's a couple ways we could have gone in the middle in terms of where we decided to cancel things out in our solving, but we should end up with the same solution at the end of x equals negative 11. It's also worthwhile to check it, make sure that does actually work. No reason not to. So you could just plug that in there, right? Negative 3 times negative 11 plus 2 equals 16 minus negative 11. So you could double check and make sure that's actually true. Here we get negative 9 times negative 3, which is 27. 16 minus negative 11, same thing as 16 plus 11, which is, yeah, 20. So it does check out. Again, that's kind of worthwhile to do. Just make sure your solution was the right one, especially you don't want to make a silly mistake when you're making a proof like this. I'll leave the other ones up to you guys. They're pretty similar. The different equations are obviously solved slightly differently, but the process is the same, using our properties of equality to come up with a solution. That was, on par with any of these other ones as far as difficulty. And now here is the big thing, the last thing that we did for this chapter, which was about making geometric proofs. These were the ones that gave people the most difficulty, and we spent a couple weeks on these. Now, the ones on the test, we chose them to be a little bit on the easier side on purpose. Didn't want them to be too confusing to you, so they're not too hard on the test. Yeah, so just make sure you're kind of looking at the different definitions, postulates, properties, theorems that you're using. How are you connecting what you started with, your hypothesis, to what you're trying to prove, that conclusion? And make sure to create that chain of reasoning. All right, so let's look at, these are just kind of listed, all the different properties and theorems and postulates and things. There's a couple other theorems that aren't on here that I'll point out here in a couple minutes, but these are some definitions, things you can do with them. I will highlight a couple of them that we use a lot to write equations, like supplementary angles and complementary angles. Those let us write a nice equation out, like two angles adding to 180 or two angles adding to be 90. We make use of that a lot. Another thing that we'll do whenever we have an angle bisector, remember that's when we have an angle that is being cut in half. So if we have an angle and we say something is a bisector, that means specifically that it cuts the angle exactly in half. So this angle and this angle would be equal to each other. Measure of angle 1 would equal measure of angle 2. That's very important whenever we have a bisector. Same thing for a midpoint. If we're told that we have a segment that has a midpoint, so right here is our segment, and a midpoint means this segment and this segment are equal, whatever they are. So in this case, we could say something like AM is equal to BM. These two paths have to be the same if M is the midpoint. Important to know, we make use of that a lot. And then in addition to that, we use all the properties of equality, and especially these two down here, the substitution property and transitive property. Those are going to be useful. Remember, transitive property is if we can create like a chain, we can say that A equals C. All right, if we know that A is equal to B, we know that A is equal to B and B is equal to C, then we can create that chain and say that A is equal to C. It's important. An example of maybe using that is something like this, like angle 1 is equal to angle 2, angle 2 is equal to 90. So then we can say that angle 1 is equal to 90, right? We can create that chain. 1 is equal to 2, 2 is equal to 90, shortcut it. Something that we'll do a lot with the transitive property. Substitution is also something that's useful. If we know two angles are equal, then we can just replace one with the other wherever we want. That's something we'll also be doing a lot. Whenever we have an equation, we may need to make substitutions into an equation. And then generally the segment addition postulate and the angle addition postulate can be used for writing an equation based on a picture about segments or about angles. We use all those things. Okay. So let's do a proof. Let's do this proof right here. I'm going to do it like a flow chart. We could do it as a 2-column proof, but I'm going to do it as a flow chart this time. Just feeling like it. So we got our givens. I want to write my givens up top. So that's going to be angle 1, angle 2 form a linear pair. I'm going to be doing this flow chart from top to bottom. I don't know exactly what the structure of it's going to look like, but just kind of getting things started. Measure angle 1 equals measure 1/3 measure angle 2. That's also given. Okay. I went and started my proof, but I'm not going to actually like jump into doing it necessarily. I want to kind of think it through. So I do notice, because we know these have a linear pair, I do know that angle 1, measure of angle 1 plus measure of angle 2 would have to equal 180, right? I can see that from my picture. I can see that because they form a linear pair. That's going to be useful. I also know, what is this? I know that measure of angle 1 is 1/3 the measure of angle 2. So this one is 1/3 the measure of angle 2. Okay. That one's tricky a little bit. And I want to prove a specific measurement for angle 1. So I need an equation that allows me to solve for angle 1 in this case. So I need to write some sort of an equation that lets me actually solve for a specific measurement for angle 1. Okay. So I'm just kind of thinking it through. We don't necessarily know exactly what it's going to look like yet. Thinking about this relationship right here, there's another way that I could write this that I think is going to be a little bit more useful to me. Instead of saying that the measure of angle 1 is 1/3 of the measure of angle 2, if I multiply both sides of this particular equation by 3, I would end up with a slightly different version of this equation. So I'm going to take this equation and I'm going to multiply both sides by 3. This is a tricky little proof. I'm pretty sure there's, yeah. So that looks like this. It becomes 3 times the measure of angle 1 is equal to the measure of angle 2. And I did that by multiplying both sides by 3. So I did multiplication property of equality. I multiplied both sides by 3. What this is going to let me do, and the reason I wanted to do this, is because now in this equation right up here, I can replace angle 2 with 3 measures of angle 1. 3m angle 1. That's going to give me this equation that only has angle 1 in it, so that I can actually solve for angle 1. The other way that it was written is I was going to be able to replace angle 1 with something about angle 2. And I think I could have gotten there that way too, but it would have taken a little longer. So I'm gonna do it this way. All right, so now I'm going to take that linear pair relationship and state that that means that they add up to 180. So measure of angle 1 plus measure of angle 2 equals 180. There is actually a theorem for this. It's called the linear pair theorem. If 2 angles form a linear pair, they are supplementary. So this is just another way for us to sort of kind of shortcut this a little bit. That's what the linear pair theorem says. If 2 angles form a linear pair, they are supplementary. And this is an equation that I can write for supplementary angles. All right, so now what I'm going to do is I'm going to take these 2 statements and I'm going to put them together. I'm going to make a substitution. And in that substitution, I'm going to write this equation that the measure of angle 1 plus 3 measure of angle 1 equals 180. Substitution property of equality. Again, this is what I'm doing here. I'm replacing angle 2 with 3 times the measure of angle 1. This now gives me an equation that only has angle 1 in it, so I can solve for the specific measure. That's why I'm doing it that way. All right, so now doing a little bit of simplifying, this equation would become 4 measures of angle 1 is equal to 180. That is just simplifying there. I added measure of angle 1 plus 3 measures of angle 1. And last step would be to take this and divide both sides by 4. Take that, divide both sides by 4. We get that the measure of angle 1 equals 45. Division property of equality. So that's a flowchart proof. More or less, the 2-column proof would look pretty similar. Uh, we would have some ability to put things in slightly different orders and still be okay. Obviously, these would be starting at the very top. Then we could say either one of these next, and then the other one after that, and then kind of following from there. The flowchart really shows what's being connected to each other and what's not. So we have 3 more minutes left. I don't want to like rush through anything else. I just want to kind of make sure everybody's clear on what this week's going to look like. Again, remember tomorrow we do not have school, and so I won't see you again until Wednesday. But Wednesday is a normal Tuesday schedule, so we will have our like whole period 4, 2, 3, 6 schedule.